In mathematics, the surreal number system is an arithmetic continuum containing the real numbers as well as infinite and infinitesimal numbers, respectively larger or smaller in absolute value than any positive real number. The surreals share many properties with the reals, including a total order and the usual arithmetic operations. As such, they form an ordered field. If formulated in von Neumann-Bernays Gödel's set theory, the surreal numbers are the largest possible ordered field. All other ordered fields, such as the rationals, the reals, the rational functions, the Levi-Civita field, the superreal numbers, and the hyperreal numbers, can be realized as subfields of the surreals. It has also been shown that the maximal class hyperreal field is isomorphic to the maximal class surreal field, in theories without the axiom of global choice. This need not be the case, and in such theories it is not necessarily true that the surreals are the largest ordered field. The surreals also contain all transfinite ordinal numbers. The arithmetic on them is given by the natural operations. In 1907, Hahn introduced Hahn series as a generalization of formal power series, and Hausdorff introduced certain ordered sets called data alpha sets for ordinals alpha and asked if it was possible to find a compatible ordered group or field structure. In 1962, Alling used a modified form of Hahn series to construct such ordered fields associated to certain ordinals alpha, and taking alpha to be the class of all ordinals in his construction gives a class that is an ordered field isomorphic to the surreal numbers. Research on the Go endgame by John Horton Conway led to another definition and construction of the surreal numbers. Conway's construction was introduced in Donald Knuth's 1974 book Surreal Numbers. How 2x students turned on to pure mathematics and found total happiness. In his book, which takes the form of a dialogue, Knuth coined the term surreal numbers for what Conway had called simply numbers. Conway later adopted Knuth's term, and used surreals for analyzing games in his 1976 book on numbers and games. Overview. In the Conway construction, the surreal numbers are constructed in stages, along with an ordering such that for any two surreal numbers A and B, either a B or BA, numbers are formed by pairing subsets of numbers already constructed. Given subsets L and R of numbers such that all the members of L are strictly less than all the members of R, then the pair L, R represents a number intermediate in value between all the members of L and all the members of R. Different subsets may end up defining the same number. L, R, and L, R may define the same number even if L, L, and R are. So strictly speaking, the surreal numbers are equivalence classes of representations of form L, R that designate the same number. In the first stage of construction, there are no previously existing numbers, so the only representation must use the empty set. This representation, where L and R are both empty, is called 0. Subsequent stages yield forms like 0 equals 1, 1 equals 2, 2 equals 3, and 0 equals minus 1 equals minus 2 equals minus 3. The integers are thus contained within the surreal numbers. Similarly, representations arise like 0, 1 equals 1/2, 0, 1/2 equals 1/4, 1/2, 1 equals 3/4, so that the dyadic rationals are contained within the surreal numbers. After an infinite number of stages, infinite subsets become available, so that any real number can be represented by La, Ra, where La is the set of all dyadic rationals less than A and Ra is the set of all dyadic rationals greater than A. Thus the real numbers are also embedded within the surreals. But there are also representations like 0, 1, 2, 3 equals omega, 0, 1, 1/2, 1/4, 1/8 equals epsilon, where omega is a transfinite number greater than all integers and epsilon is an infinitesimal greater than 0 but less than any positive real number. Moreover, The standard arithmetic operations can be extended to these non-real numbers in a manner that turns the collection of surreal numbers into an ordered field, so that one can talk about 2 omega or omega minus 1 and so forth. Construction. Surreal numbers are constructed inductively as equivalence classes of pairs of sets of surreal numbers, restricted by the condition that each element of the first set is smaller than each element of the second set. The construction consists of 3 interdependent parts: the construction rule, the comparison rule and the equivalence rule. Forms. A form is a pair of sets of surreal numbers, called its left set and its right set. A form with left set L and right set R is written L, R. When L and R are given as lists of elements, the braces around them are omitted. Either or both of the left and right set of a form may be the empty set. The form, with both left and right set empty, is also written. Numeric forms. Construction rule. A form L, R is numeric if the intersection of L and R is the empty set and each element of R is greater than every element of L, according to the order relation given by the comparison rule below. Equivalence classes of numeric forms. The numeric forms are placed in equivalence classes. Each such equivalence class is a surreal number. The elements of the left and right set of a form are drawn from the universe of the surreal numbers. Equivalence rule. 2 numeric forms X and Y are forms of the same number if and only if both X, Y and Y X. An ordering relationship must be antisymmetric, i.e., it must have the property that X equals Y only when X and Y are the same object. This is not the case for surreal number forms, but is true by construction for surreal numbers. The equivalence class containing is labeled 0, in other words, is a form of the surreal number 0. Order. The recursive definition of surreal numbers is completed by defining comparison. Given numeric forms X equals XL, XR, and Y equals YL, year XY if and only if there is no XL such that YXL, and there is no year such that year X. A comparison YC between a form Y and a surreal number C is performed by choosing a form Z from the equivalence class C and evaluating YZ, and likewise for CX and for comparison BC between 2 surreal numbers. Induction. This group of definitions is recursive, and requires some form of mathematical induction to define the universe of objects that occur in them. The only surreal numbers reachable via finite induction are the dyadic fractions. A wider universe is reachable given some form of transfinite induction. Induction rule. There is a generation S0 equals 0, in which 0 consists of the single form. Given any ordinal number n, the generation Sn is the set of all surreal numbers that are generated by the construction rule from subsets if. The base case is actually a special case of the induction rule, with 0 taken as a label for the least ordinal. Since there exists no C with I less than 0, the expression is the empty set. The only subset of the empty set is the empty set, and therefore S0 consists of a single surreal form, lying in a single equivalence class 0. For every finite ordinal number n, Sn is well ordered by the ordering induced by the comparison rule on the surreal numbers. The first iteration of the induction rule produces the 3 numeric forms 0, less than 0. The equivalence class containing 0 is labeled 1 and the equivalence class containing 0 is labeled -1. These 3 labels have a special significance in the axioms that define a ring. They are the additive identity, the multiplicative identity, and the additive inverse of 1. The arithmetic operations defined below are consistent with these labels. For every I less than n, since every valid form in C is also a valid form in Sn, all of the numbers in C also appear in Sn. Numbers in Sn that are a superset of some number in C are said to have been inherited from generation I. The smallest value of alpha for which a given surreal number appears in S alpha is called its birthday. For example, the birthday of 0 is 0, and the birthday of -1 is 1. A second iteration of the construction rule yields the following ordering of equivalence classes. -1 equals -1, 0 equals -1, 1 equals -1, 0, 1 less than 0 equals 0, 1 less than -1, 0 equals -1, 0. 1 less than equals -1 equals 1 equals -1, 1 less than 0, 1 equals -1, 0, 1 less than 0 equals -1, 0 less than 1 equals 0, 1 equals -1, 1 equals -1. 0, 1. Comparison of these equivalence classes is consistent irrespective of the choice of form. 3 observations follow. S2 contains 4 new surreal numbers. 2 contain extremal forms. -1, 0, 1 contains all numbers from previous generations in its right set, and -1, 0, 1 contains all numbers from previous generations in its left set. The others have a form that partitions all numbers from previous generations into 2 non-empty sets. Every surreal number x that existed in the previous generation exists also in this generation, and includes at least one new form. A partition of all numbers other than x from previous generations into a left set and a right set. The equivalence class of a number depends only on the maximal element of its left set and the minimal element of the right set. The informal interpretations of 1 and -1 are the number just after 1 and the number just before -1, respectively. Their equivalence classes are labeled 2 and -2. The informal interpretations of 0, 1, and -1, 0 are the number halfway between 0 and 1, and the number halfway between -1 and 0, respectively. Their equivalence classes are labeled 1/2 and -1/2. These labels will also be justified by the rules for surreal addition and multiplication below. The equivalence classes at each stage n of induction may be characterized by their n-complete forms. Either this complete form contains every number from previous generations in its left or right set, in which case this is the first generation in which this number occurs, or it contains all numbers from previous generations but one, in which case it is a new form of this one number. We retain the labels from the previous generation for these old numbers, and write the ordering above using the old and new labels. -2 less than -1 less than -1/2 less than 0 less than 1/2 less than 1 less than 2. The third observation extends to all surreal numbers with finite left and right sets. The number 1, 2, 5, 8 is therefore equivalent to 2, 5. One can establish that these are forms of 3 by using the birthday property, which is a consequence of the rules above. Birthday property: a form x equals L, R, occurring in generation n represents a number inherited from an earlier generation I less than n if and only if there is some number in C that is greater than all elements of L and less than all elements of the R. If x represents a number from any generation earlier than n, there is a least such generation I, and exactly one number C with this least I as its birthday lies between L and R. X is a form of this C. It lies in the equivalence class in Sn that is a superset of the representation of C in generation I. Arithmetic. The addition, negation, and multiplication of surreal number forms x equals xl, xr, and y equals yl, year, are defined by 3 recursive formulas. Negation of a given number x equals xl, xr is defined by where the negation of a set S of numbers is given by the set of the negated elements of S. This formula involves the negation of the surreal numbers appearing in the left and right sets of X. which is to be understood as the result of choosing a form of the number, evaluating the negation of this form, and taking the equivalence class of the resulting form. This only makes sense if the result is the same irrespective of the choice of form of the operand. This can be proven inductively using the fact that the numbers occurring in XL and XR are drawn from generations earlier than that in which the form X first occurs, and observing the special case -0 == 0. Addition. The definition of addition is also a recursive formula, where this formula involves sums of one of the original operands and a surreal number drawn from the left or right set of the other. These are to be understood as the result of choosing a form of the numeric operand, performing the sum of the two forms, and taking the equivalence class of the resulting form. This only makes sense if the result is the same irrespective of the choice of form of the numeric operand. This can also be proven inductively with the special cases 0 plus 0 equals 0 x plus 0 equals x plus xl plus 0 xr plus 0 equals xl xr equals x0 plus y equals y equals 0 plus yl 0 plus year equals yl year equals y. Multiplication. The recursive formula for multiplication contains arithmetic expressions involving the operands and their left and right sets, such as the expression that appears in the left set of the product of x and y. This is to be understood as the set of surreal numbers resulting from choosing one number from each set that appears in the expression and evaluating the expression on these numbers. This depends, in turn, on the ability to multiply pairs of surreal numbers drawn from the left and right sets of x and y to get a surreal number, and negate the result. Multiply the surreal number form x or y and a surreal number drawn from the left or right set of the other operand to get a surreal number, and add the resulting surreal numbers. This again involves special cases, this time containing 0 equals, the multiplicative identity 1 equals 0, and its additive inverse -1 equals 0. Consistency. It can be shown that the definitions of negation, addition and multiplication are consistent, in the sense that addition and negation are defined recursively in terms of simpler addition and negation steps, so that operations on numbers with birthday n will eventually be expressed entirely in terms of operations on numbers with birthdays less than n. Multiplication is defined recursively in terms of additions, negations, and simpler multiplication steps, so that the product of numbers with birthday n will eventually be expressed entirely in terms of sums and differences of products of numbers with birthdays less than n. As long as the operands are well-defined surreal number forms, the results are again well-defined surreal number forms. The operations can be extended to numbers. The result of negating x or adding or multiplying x and y will represent the same number regardless of the choice of form of x and y, and these operations obey the associativity, commutativity, additive inverse, and distributivity axioms in the definition of a field, with additive identity 0 equals, and multiplicative identity 1 equals 0. With these rules one can now verify that the numbers found in the first few generations were properly labeled. The construction rule is repeated to obtain more generations of surreals. S0 equals 0, S1 equals -1 less than 0 less than 1, S2 equals -2 less than -1 less than -1 half less than 0 less than 1 half less than 1 less than 2, S3 equals -3 less than -2 less than -3 halves less than -1 less than -3 quarters less than -1 half less than -1 quarter less than 0 less than 1 quarter less than 1 half less than 3 quarters less than 1 less than 3 halves less than 2 less than 3, S4 equals, -4 less than -3 less than -1/8 less than 0 less than 1/8 less than 1/4 less than 3/8 less than 1/2 less than 5/8 less than 3/4 less than 7/8 less than 1 less than 5/4 less than 3 halves less than 7/4 less than 2 less than 5 halves less than 3 less than 4. Arithmetic closure for each natural number n. All numbers generated in Sn are dyadic fractions, i.e., can be written as an irreducible fraction where a and b are integers and 0 b less than n. The class of all surreal numbers that are generated in some Sn for finite n may be denoted as S** equals. One may form the three classes S0 equals 0, S plus equals, and S equals, and state that S** is the union of these three classes. No individual Sn is closed under addition and multiplication, but S** is. It is the subring of the rationals consisting of all dyadic fractions. At an appropriate stage of transfinite induction, the surreal numbers may be expected to form a category on which the addition and multiplication operations are closed, and in which the multiplicative inverse of every non-zero number can be found. Assuming that one can find such a class, the surreal numbers, with their ordering and these algebraic operations, constitute an ordered field, with the caveat that they do not form a set but a proper class. In fact, it is a very special ordered field, the biggest one. Every other ordered field can be embedded in the surreals. The class of all surreal numbers is denoted by the symbol